Hey everybody, welcome back. Today we're going to go over a manufacturing process analysis program that I wrote, and this uses a graph theory to optimize production workflow. So the part that I have shown on the screen is a real part from a production process I dealt with a long time ago. The times are arbitrary, roughly, and some of the process was a little more granular than this, but this is kind of an overview, a rough overview of a real production process. And what we're going to be doing is looking at the critical path of this process. Now, Dijkstra's algorithm is typically used to look at the shortest path. Be something used like Google Maps or Garmin or Apple Maps. So this program is going to look at 3 parallel production paths that converge for final assembly and finishing. And we're going to be using NetworkX, a professional Python library for graph analysis. We're going to analyze the critical path, the process flow, and identify some key production bottlenecks. So let's do a quick code review. So we created a directed graph using NetworkX's digraph class. And this defines 23 manufacturing tasks with respective durations. And in this case, we're using hours. And we're going to connect these tasks with 26 edges representing dependencies. So for the critical path analysis, we're using a modified Dijkstra's algorithm to find the longest path. And this identifies the sequence of tasks that determine the minimum completion time. Then we're doing a breadth-first search, and this explores the manufacturing process level by level, and it shows how tasks are discovered in sequence. And then finally, we're going to do a centrality analysis. This calculates degree in betweenness centrality, and this identifies the most critical tasks in the workflow. So then we run the program, and we take a look at the results. So the critical path identifies the rubber blending pathway as the critical path, and it runs through the rubber processing route. And the total manufacturing time is 94 units, which would be hours. And we can see that the key bottlenecks are injection molding with 18 hours, calendar rubber sheets 14 hours, and paint and finishing is 14 hours. Now the BFS output shows pairs of connected nodes or tasks in the format of task A pointing towards task B. So at the top, we look at the first one, start, and then arrow to create work order. And this is representing the order in which the tasks are discovered, exploring the graph level by level from the start node. And this is not a measure of time or duration, but rather shows the connectivity and the hierarchy of tasks in the manufacturing process. Then when we get into the centrality analysis, the centrality measures are expressed as normalized values between 0 and 1. So with the degree centrality, this measures how many direct connections a task has to other tasks. Higher values closer to 1 indicate tasks that interface with many other tasks. For example, assemble components for injection molding would have higher degree of centrality as it connects to multiple parallel paths. And then with betweenness centrality, this measures how often a task acts as a bridge between other tasks, and higher values indicate tasks that are crucial bottlenecks or integration points. So tasks like injection molding operation would have higher betweenness centrality. All paths must flow through it to reach completion. So these metrics help identify which tasks are most critical to the overall process flow, not in terms of duration, but in terms of their structural importance in the manufacturing sequence. So that was a quick overview. If you have any questions, please hit the like button, leave a comment below, and I will see you all next time.